now we move into chapter 6, where we're going to start putting things together. We're going to start taking Newton's laws and looking at calculating accelerations. So remember, Newton's first law says for an object that is at rest to remain at rest, and for an object in motion to remain in motion with a constant velocity, the sum of the forces acting on the object must be 0. This is referred to as in equilibrium. One of the things I want to point out to you right now is that an object could be in equilibrium along one axis but experience motion along another. Okay, always keep that in the back of your mind. So remember, there's two forms of equilibrium: static equilibrium and dynamic equilibrium. In static equilibrium, the sum of the forces is 0 and the velocity is 0. In dynamic equilibrium, the sum of the forces is 0 and the object's velocity is a constant. Okay? So, we know when an object is in equilibrium, the sum of the forces are in equilibrium, or the sum of the forces equals 0, which means the acceleration will be 0. So since we live in a 3D world, to be in total equilibrium, sum of the forces in the x direction have to be 0, sum of the forces in the y direction equals 0, sum of the forces in the z direction have to be 0. If the sum of the forces along any axis is 0, then there is an equilibrium along that axis. Okay? So let's do a static equilibrium problem. So we're going to look at problem 1 at the end of the chapter. Okay? So chapter 6, problem 1 at the end of the chapter. Now let's read the problem over. I'm going to show you the picture, and then we're going to draw it and work it. I know. I'll get it into the right position, don't worry. Okay, here we go. Problem 1. It says the 3 ropes in figure 6.1 are tied to a small, very light ring. 2 of these ropes are anchored to the wall at right angles, and the tensions shown. What is the magnitude and direction of force 3 in the 3rd rope? Okay? So, first thing we've got to do is draw a free body diagram, and the ring is our object. Okay? So we are looking at this bird's eye view, guys. Okay, bird's eye view. Let me see something here. Can I? Ooh, I have learned something. Ah! Stop. I blew it up too big. Stupid thing. Oh well, I'll eventually get it set. Well, that's not any good. Okay, let me draw a picture. Okay, guys, the computer and I are not working. All right, let's just switch over to the computer. All right, now let me slide this over and see what we can get. Okay, so if we look at it, there is a force acting on the ring to the left, and it's a 50 Newton force. Okay, And there is a force along the y-axis that's an 80 Newton force. And then we've got a force T here, which we don't know. Well, think about this. There's going to be a TX force and a TY force. Sum of forces in the x direction has to equal TX plus a minus 50 Newton force, and that has to sum up to be 0. 50 is pointing in the minus x direction. Okay, so that means that TX has to be plus 50 newtons. Sum of forces in the y direction has to be TY plus 80 newtons, which also has to sum up to be 0. Because I'm summing x-axis and y-axis, notice I'm not using the ij vectors. Since we have them broken up separately, most people don't use the I and the J right now. So notice Ty here is a minus 80 newtons. The negative sign because Ty is pointing in the negative y direction. Okay, so that means the magnitude of our vector T would just be the square root of 50 squared plus 80 squared. Both of those, and my answer will be in newtons. And our angle theta here would just be the inverse tangent of 80 over 50. Now, I forgot to bring my calculator in here. I'm going to let you guys finish that off on your own. Okay, so that's example 1. Now we're going to look at problem 4. Okay? No, let's look at problem 3. Now I'm going to read problem 3 to you because that stupid camera is not working with me. It just keeps getting stuck. Well, I'm going to give it one more try. Let's see what happens when I try to get question 3. Okay. I'm going to leave it as it sits right now. Yeah, that's good. Let's look at the problem. Okay. The problem reads, the football coach sits on a sled while 2 of his players build their strength by dragging the sled across the field with ropes. The friction force on the sled is 1,000 newtons, and the players have equal pulls, and the angle between the 2 ropes is 20 degrees. How hard must each player pull to drag the coach at a steady 2 meters per second? Now, because it says steady 2 meters per second, that tells me that we're in dynamic equilibrium, okay? So let's start drawing a picture here. Hold on a second, I'm going to get a little bit ahead of you. Give you a chance to read over the problem. Okay. Now, there's our axes. The dot right here, that's the sled, okay? We're told in the problem that there is a frictional force of 1,000 newtons, and then we have 2 players pulling with equal force. So I have a tension 1 here and a tension 2. Now, I wanted to make my motion in the positive x direction because I'm just that way, and it didn't tell me which, so I could draw it any way I wanted to. And there's our frictional force. And it's a kinetic frictional force because it tells me that the cart is moving. Okay? Now, the kinetic frictional force, F sub k, has a magnitude of 1,000 newtons. we're told that this angle is 20 degrees. So that means that's 10 degrees and that's 10 degrees. So if I start breaking things up into x and y components, I've got a T1x and a T1y. And then I've got a T2x and a T2y. Now, if we read the problem, it says the players pull with equal force. So I know that the magnitude of T1 equals the magnitude of T2 because they're pulling with equal force. Okay? Now, the sum of forces in the y direction is T1y plus T2y, which equals 0. That doesn't do me a whole lot of good. If we look at the sum of forces in the x direction, I have the frictional force, T1x, and T2x having to add up to be 0. So our frictional force is pointing in the negative x direction. So I have minus 1,000 newtons plus T1x plus T2x having to be 0. Now, here's where a little bit of physics and math come together. T1 and T2 both have the same magnitude. I'm just going to call it T. I know that T1x in magnitude is equal to T cosine of 10 degrees. Also know the magnitude of T2x is going to be T cosine 10 degrees. So let's play with this a bit. Okay, I'm going to go up high. So I have minus 1,000 newtons plus T cosine 10 degrees plus T cosine 10 degrees. These are both positive because T1x and T2x point in the positive direction equals 0. So I have 2T cosine 10 degrees is equal to 1,000 newtons. So T cosine 10 degrees is equal to 500 newtons. So T in magnitude is going to be 500 newtons divided by the cosine of 10 degrees. Again, you guys can finish out the math by plugging it into your calculator. Okay, so a straightforward problem. The reason I like this one is we have to start breaking our forces up into x and y components and think about the way things are related. Okay? Now, I think you're starting to get the idea about sum of the forces adding up to be 0. I think you can do those problems without me now. So, one of the things then we have to start paying attention to is thinking whether an object is in equilibrium or not, and if it's in equilibrium in one direction, is it in equilibrium in another direction? Okay? We want to always think about dividing things up into x and y components. So I have here for us to look at problem 8 at the end of the chapter. I think, yeah, we can look at problem 8. I'll help you set it up. Okay? So let's look at problem 8. We look at problem 8. There. Problem 8 goes with figure 6.8. And problem 8 says The forces in figure 6.8 act on a 2 kilogram object. What is the value of the acceleration in the x direction, the acceleration in the y direction, the x and y components of the object's acceleration? So here we're given an object and we're asked to find its acceleration. So let's look at summing things up. Okay? So you guys look at that, do your free body. Where did the camera go? Our display went off. Okay, let's see if I can go back to the doc cam. All right, I'm going to do a drawing, guys. And I'm going to put all those forces on it. All right. Let's look at my drawing here. Oh, I didn't show you the original. Guys, there's the original. Okay? Make sure you've got it. I'm sorry I didn't move the screen over, but you can see the original drawing. Okay? Now let's go over here. One of the things I want you to notice in this original drawing is they were very sneaky, and if I called this a force T, they gave us Ty was 3 newtons, and they gave us Tx is equal to 4 newtons. So if I did the sum of the forces in the x direction, I'd have a plus 2 newtons plus a minus 4 newtons, which would sum up to a minus 2 newtons. Form the forces in the y direction would be a plus 3 Newton force plus a minus 3 Newton force, which is 0. Okay? I have an equilibrium in the y direction. The only net force we have is in the x direction. So acceleration in the y direction is 0. Acceleration in the x direction is going to be the force, net force in the x direction, minus 2 newtons, divided by the mass of the object, and we were told that it was a 2 kilogram object. So that gives me a minus 1 meter per second squared. The negative means minus x direction. So our acceleration, A, is just going to be minus, well, it's going to have a magnitude of 1 meter per second, and we can say that it's along the negative x axis. Okay? So I like that problem because it gave you an example where the sum of the forces along one of the axes was 0. Now, the other problem I have picked out is problem 12. So we're going to look at problem 12. So let's look at problem 12 here. Okay, it says a horizontal rope is tied to a 50 kilogram block box on frictionless ice. It says, what is the tension of the rope if the box is at rest? Well, if we're taking a bird's eye view, guys, okay, force due to gravity and the normal force are not going to be into play because we are looking at it bird's eye. If the box is at rest and it's on a frictionless surface, then the tension in the rope has to be 0. If you applied any pull at all to the box, it would move. Okay, it says the box is moving at a steady 5 meters per second. Now, the key word there, guys, is steady. Since it's experiencing a steady velocity, a steady speed, then the box is in dynamic equilibrium, and again, the rope has to be applying 0 tension. C says the box has a velocity Vx of 5 meters per second and a velocity AY of 5 meters per second squared. In C, there's an acceleration. So in C, we have to have a force. Okay, so let's draw a pretty picture here. So if the dot is my box, and there's my plus X, there's my plus Y, and the rope is applying a tension, Tx. Okay? I know that in this direction I have an acceleration of 5 meters per second squared. So I didn't write the velocity in here because it's not as critical to what we're trying to do as the acceleration. So I know the sum of forces in the x direction is just going to be Tx, and that has to equal whatever the mass of the object is times the acceleration in the x direction. Now, it told us in the problem that it was a 50 kilogram box. So Tx is going to equal 50 kilograms times the acceleration of 5 meters per second squared. So we're going to end up with a force of newtons. 5 times 5 is 25, so that's 250 newtons. I can do that without a calculator. Okay, and it's in the plus x direction the way I have it drawn. So that's not too bad, right? We can handle that. Now, let's talk about force due to gravity for a minute. I get done with force due to gravity, I'm going to close this lecture down. Okay, because I'm going to have to switch out batteries. All right. Force due to gravity, F sub g, gravitational force is the pull of the earth on an object. Gravitational force is a force at a distance. Okay? And it's there whether an object is touching the earth or not. Newton was really one of the first people to realize that there's a gravitational force between any two objects that have mass. The earth exerts a gravitational force on all of us, and we exert a gravitational force on the earth. These two forces are equal in magnitude, opposite in direction. You exert a gravitational force on a person sitting next to you, or on your pencil, or on the chair, the TV, okay? But because we have very little mass, and a pencil in the grand scheme of things has very little mass, the gravitational force is very, very tiny. Force due to gravity between any two objects can be calculated as big capital G times the mass of object 1 times the mass of object 2 divided by r squared. Now, if big M is the earth, then the force due to gravity when we as an object interact with the earth is our mass times G, big G times big M over r squared. If you take big G times big M over r squared, and you're staying fairly close to the surface of the earth, you get little g. which is 9.80 meters per second squared. And that works as long as we're within 10 kilometers of the surface of the Earth. So for us, for right now, force due to gravity is equal in magnitude to m, the mass of the object we're interested in looking at interacting with the Earth, times g. Okay? So let's define weight. I know I defined it last chapter, but here we go again. Weight W is what a scale measures, or what a scale reads. Okay, as long as we are sitting on the surface of the Earth, and we are not, or we're sitting in a building, we're not moving up, we're not moving down, okay, weight is going to equal force due to gravity. So, weight is often measured in terms of a compression of a spring. So there's going to be a spring force is going to be the way that we're going to measure force due to gravity on an object. So weight is what a scale reads, a force due to gravity. So we can say that for an object that is sitting still, force due to gravity and force from the spring equals 0. Force due to gravity is going to be minus mg. The force of the spring we call weight is equal to 0. So weight is going to equal just mg. So let me show you an example problem here. Okay. So here's our elevator. Whee! And we have a scale here. And we have a person, whee, standing on the scale. Okay? The mass of our person, let's say, is 70 kilograms. And the acceleration of the elevator is equal to 0. So force due to gravity is minus 70 kilograms times 9.80 meters per second squared. And the sum of forces in the y direction, okay, we have the force of the spring, which we can call weight, force due to gravity, pulling down. If I took the sum of forces in the y direction, force due to gravity, plus force of the spring, have to equal 0. Then I have minus 70 kilograms times 9.80 meters per second squared, plus force of the spring, having to equal 0 for the force of the spring, is just the 70 kilograms times 9.80 meters per second squared. It's around 700 newtons. It'll be a little bit less, but remember I forgot my calculator. Okay? Now let's go to case 2. In case 2, let's have our car, our elevator, accelerating upward. So let's have our car accelerating up at 2.00 meters per second squared. Now the net force is force due to gravity plus the force of the spring is equal to mg. So I have minus mg plus w equals ma. So our weight is going to be mg plus ma. Okay? So if I'm dealing with my same person, now I have an acceleration that's in the positive direction. Now I just worked out the equation for you. weight here is going to be mg, which was 70 kilograms, times 9.80 meters per second squared, plus 70 kilograms times 2 meters per second squared. So it's going to be equal to 70 kilograms times 11.8 meters per second squared. So notice that the weight, what that scale is going to read, is now going to be larger than what it was if you had the elevator sitting still. That's why your stomach feels like it's dropping out on you when you are in an elevator that's accelerating very quickly upward. Now, I have done the math for you here. Okay? So you can see it right there. And now let's look at a case 3. Okay, where we're accelerating downward. So if we're accelerating downward, okay, working through the same thing, sum of the forces in the y direction would be force due to gravity, force of the spring equals ma. So I have I minus mg plus w equals ma. So w equals mg plus ma. So now I have an acceleration where a is the magnitude that's pointing down. So I have mg minus a. Okay, there's the negative. And if we do this, the scale's going to read 585 newtons. It's going to be less. This is why if you're in an elevator that's going down very fast, it feels like your stomach's kind of coming up into your throat. Okay? Now, but you can see moving up, the weight's going to be greater than if it was sitting still on the earth. Moving down, it's going to be less. So if we took this to the ultimate extreme, what if our acceleration downward was 9.80 meters per second squared? What would the weight be? It would be 0. Okay? So if something is falling with an acceleration due to gravity, the weight is 0. So if I was in an elevator that was falling at acceleration due to gravity and I was to let go, let's say, of my book would not move up or down relative to where it was when I let go of it. Of course, I would be screaming my head off because I'd be in a lot of trouble, but the book wouldn't move up, the book wouldn't move down relative to my position. So what a scale reads depends on what kind of motion you're undergoing. Okay? Weightlessness, like we see for astronauts on the International Space Station, is when an object is falling toward the Earth with an acceleration of 9.80 meters per second squared. It doesn't mean that they're not experiencing any gravitational force from the Earth, but if they were standing on a scale, the scale would read 0 because they're in free fall. Your book calls it weightlessness, other book calls it apparent weightlessness, but if you define it as what a scale reads, they would be weightless. Doesn't mean they're not experiencing a force due to gravity. Okay? So, they're experiencing a force due to gravity, but they have no quote-unquote weight. They still have mass. All right, guys, it's a good place for me to end this before we move on to the